Mhm. Okay. So today we will start with the main and very important theorem that the projective varieties are proper or complete in some other terminology. And this means that let's say if X is a projective variety, and Y an arbitrary variety, then the projection from X times Y to Y is closed. So the image of any closed subvariety Z in this product, the image of the Z in Y is also closed. Okay. Or in other words, the projection per Y is proper. So this property of being proper is a property of morphisms, actually not of varieties, but here I mean the projection from X to a point is proper. Okay, so let's first see sort of counter example. So say if X is the same as Y and is just the affine line, and Z inside the product, that is inside the affine plane, is given by the single equation xy equals 1. So it's a hyperbola. Okay, then suddenly it's closed, but the image under projection to y of z is certainly a set of all non-zero numbers. So it's not closed. In fact, it's open. Okay, so you see that in this terminology, x equals a1 is not proper or complete. Okay, and while we are here, let's consider another counter example or example, maybe, I don't know. So let's consider a morphism from A2 to A2. And here the coordinates x and y go to x and xy. Okay, so it's a certain extension of the previous example. Yeah, I just add one more coordinate to the image. And then what is the image of this morphism? Let's call it pi. So you see, if say well, let me put it this way. These are pairs ZT, such that say if none of them is zero, then certainly it's in the image. Okay. Now, if Z is zero, then necessarily T is also zero. Okay, and that's it. So if Z is zero, then T is zero. Okay, so how does it look like? Let me draw a picture. So there's our T coordinate, this is our Z coordinate, and if Z is zero, then T is zero as well. So you see, we don't. Well, let me maybe draw it another color. So this part is removed, and this part is removed, but the origin is in there. Sorry, I want to. Okay, so the origin is in there. So how to say it? It's a plane without the vertical axis, but with the origin. Okay, so it's neither closed nor open. Okay, and not even locally closed. Okay, what it is, it's so-called constructible. So it is a union, say finite union of locally closed subvarieties. Okay, and there is a general theorem due to Claude Chevalier. That the image of any morphism of algebraic varieties is always constructible. Okay, but the theorem I'm going to prove now, our main theorem for today, says that in case of projective morphism, it's much better. The image is just closed. Okay.
Excuse me, what is projective morphism?
I will say it momentarily. For projective morphism, the image is closed. Now, what is a projective morphism? Let's consider, say, y times projective space, and inside, let's consider any closed Z. Okay, and there is a projection morphism to Y here, and there is a composition like this. Okay, and this diagonal composition is called projective. Okay, so it's just an immediate corollary of our main theorem. Let's go back for a moment. This main theorem says that no, it didn't say anything yet. Yeah, the main theorem didn't say anything yet. It was only definition of a complete or a proper variety, right? And now the main theorem that we are going to prove right away says that the projective space is a proper variety. Okay. Okay, and immediate corollary is that any projective variety is proper. I mean, any closed subvariety of projective space is a proper variety. Okay, and maybe before I prove it and before I forget, let me formulate another sort of corollary or maybe basic property. Is that any regular function on a proper variety is constant. So in some early exercise, you proved that any regular function on the projective space itself is necessarily constant. Yeah, but now it applies to any projective subvariety and to any proper variety at all. So let's prove this basic property first, and then finally we'll prove this much advertised theorem. So let's consider a function, say f on our proper variety, and let's assume it's not zero. Well, if it's zero, then it's already constant. Yeah, so we may freely assume that it is not identically zero, and then we can consider its the open subset where it's not zero. It will be a non-empty open subset. Maybe in fact I should add that this proper variety is connected, or at least irreducible on an irreducible. Otherwise, I could have functions constant on various connected components with different values. Okay, so now df is a dense non-empty open subset in X.
Почему оно плотное?
And yes.
Почему оно плотное?
It is dense because I have just assumed that that my variety X is irreducible. So any open subset is dense, okay, just due to the assumption. Okay, so on this open subset, I can consider the function 1 over f, and let's consider the graph of 1 over f. Okay, gamma 1 over f. It sits inside df times a1 and sits inside x times a1 and is cut out by the equation f times t equals 1, right? Just a single equation. And hence, you see, it's well defined on the whole of x. So initially, this graph lies in the open subset df times a1, but after you see this equation, it's defined on the whole of x, and it's a closed subvariety. Gamma f is closed in x times a1. But since x was assumed to be proper, it means that
Excuse me, not gamma f, but gamma 1 divided by f.
Oh yes, thank you. 1 over f. Thank you. So it means that the projection of this graph to a1 is closed in a1, but it does not contain 0, certainly. It misses 0 inside a1. So just by definition of the Zariski topology, it is it must be a finite collection of points. But since this thing is irreducible, it must be just a single point.
Why is this thing is irreducible?
Why is this graph irreducible? Just because it is isomorphic to df, right? It's a graph of function of points, but gamma 1 over f is isomorphic to df, so irreducible. And hence this projection of the graph is just a single point. I don't know, p. And hence 1 over f is equal to p. And hence f is identically equal to p inverse. So f is constant. That's what I wanted to prove. Okay, so now let's prove the main theorem. So once again, we want to prove that Pn is proper. And we consider the projection Pn times y to y, and we can cover, as always, our base y by affine subvarieties. Open cover of y, and then we see that the question is local on the base y, and So it suffices to prove our theorem for y affine, and that's what we are going to do. So we have closed subvariety in Pn times y, and we're going to prove that its projection onto y is closed. And it means it is given inside inside y is given by finitely many equations, just regular functions on y.
Почему важна конечность? Почему не может быть бесконечное число, например?
Well, by Noetherian property, it is automatic.
But by definition, we can use not global functions, but some local functions for the
yes, but now I assume that y is affine, so so the closed subvariety is given by some global equations, and in fact it suffices to use finitely many. But again, in principle, that's not necessary. Okay, and in fact we will exactly construct infinitely many equations, but then by Noetherian property, finitely many of them will suffice. Okay, so let's do this.
Sorry, is this true that that our projection morphism is affine, and that's why it's closed? I don't understand why it's closed.
That's what I have to prove.
It's not evident. Sorry.
Yeah. That's the content of the theory. We have to prove that the image is closed.
Okay.
Okay. Okay. So let's do this. Let's prove. Let's prove some lemma. So inside how to say it, the homogeneous ring functions on y, and then the homogeneous coordinates on this projective space. So x0 and so on, x capital N. There are finitely many polynomials, say f1 and so on, f L, or maybe FL, homogeneous in these coordinates x0 through xn, such that z is cut out by equations f1 equals so on equals fl equals 0. Okay, so you see, we should view our z as a in fact we should view the whole thing. We have this y times Pn. And there's a family of projective spaces over the base y. Okay, and now in each fiber we have a closed subvariety z. There is fiber y times Pn, and inside we have the fiber z sub y. Okay, and it is just a closed subvariety of projective space Pn. So by definition, it is given by subhomogeneous equations. But now I claim that those homogeneous equations could be written down somehow simultaneously for all points. Okay, so uniformly in y. Okay, that's what I claim, and this is more or less clear. So why is it so? Let's consider the cone. So this is the proof of this lemma. The cone, say CZ, and this is the closure of the preimage, say, identity of y times the projection from the affine space n+1 without the origin to the project space, but then we add the origin to this cone. Okay, and then the dilations group the multiplicative group GM acts on this cone just as before, and hence on its ideal J CV inside the ring of functions. And hence JCZ admits an eigenbasis with respect to this action okay, and we just take the homogeneous components of the generators of this ideal. Okay, for the generators F1 and so on through FL. Okay, so the lemma is proved, and we know that we can cut out our closed subvariety Z by some homogeneous equations somehow uniformly over the base Y. Okay, now we're going to use this lemma and to finish the proof of the theory. So the equations that will cut out the image of this Z under projection to Y will be certain determinant equations So if they will say that the rank of certain matrices will be less than full rank. So in other words, certain linear map or maps will be not surjective. Okay, and to this end, let me specify the degrees. So the degree of Fi will be denoted by di, and we have say the space, maybe let me note S di will be the space of polynomials of this degree di in how to say it, in the variables x1 and so on, as x0 and so on, x capital N. Okay, so there's polynomials of degree di in n+1 variables. Okay. Now we can take such a polynomial and multiply it by any other. But no, sorry. Inside here we have fi, f sub I. Okay. And now we can multiply this f sub I by any other polynomial. By fi is a linear operator from S anything, say n, to S n plus di. Okay, and if we just add up all such multiplication operators, we obtain a map beta, linear operator beta, from the direct sum from g equals 1 to L as say n minus or n minus dj tensor functions on y to Sn tensor functions on y. Okay, so I take the elements here. So let me denote them H1 and so on, HL. They go to H1 times F1 plus so on plus HL times FL. Okay, and the degrees here match. Yeah, I take degree n minus dj, then I multiply polynomial of this degree by fj that has degree dj, and so you end up in the symmetric algebra polynomials of degree n. Okay, fine, and then say En. This is a subvariety in Y. It is the subvariety of parameters and is given by equation, that this map is not surjective, so that the rank is not full. Maybe let me denote it by beta sub n, that beta sub n is not surjective. That is, all the minors of rank dimension of Sn vanish. Okay. So it is a closed subvariety in Y. So N and Y is a closed subvariety given by explicit polynomial equations, vanishing of some minors of this matrix. Okay. Now I claim that the desired projection image of Z is the intersection of all those subvarieties over all n. Okay, positive integers, and that's enough because all those are closed, and the intersection of family of closed subvarieties is closed, and there we are. But then by Noetherian property, we know that actually we need only some finite intersection. Okay, so we have to prove this claim, and let's prove it. And this is just the projective Nullstellensatz.
Do we even need to have finite amount of these ENs, because we know that any intersection of like even infinitely many of them will be closed?
Yes, certainly. You don't need any finiteness here. You're absolutely right. But just it's maybe pleasant or nice to know that this intersection is actually finite. That is given that this image is cut out by finitely many equations. Yeah, there's nothing extra in it. It just follows automatically by Noetherian property, but still maybe nice to know. Okay, so what does this projective Nullstellensatz, we proved last time, say? It says that a point lies in this image of projection if there is something over it. Yeah, there is no non-empty fiber over it. It's not a project Nullstellensatz, just definition. But now this means again there is no projective Nullstellensatz here. It means that our equations f1 of y and x equals so f l of y x is 0. This level set is not empty. Okay, but now by project Nullstellensatz, finally, this is equivalent to the fact that beta n of y is not surjective for all positive integers. Okay, and then again, by definition, it means that y lies in the intersection of all those E sub n over all positive integers, and we're done. Okay, so we have crucially used this at this point here. The project was telling that. Okay, so the theorem is proved, and it's very important and will be used throughout the whole course, and we will see many applications, but let's talk first about ubiquity of projective varieties among proper varieties. So we proved that all the projective varieties are proper. Okay, and now sort of converse is given by Chow lemma. So it says that any proper variety is say more or less projective, or more rigorously, it is birationally isomorphic to a projective variety. Oops, sorry. And what does this mean? It means that say let's call it y, this y, and there is a projective variety x, and or maybe again, let's assume that everything is irreducible here. So it's reducible, and this one is also reducible. And then there are open subsets. Say U in X and V in Y that are isomorphic. Okay, so this is the notion of birational isomorphism. For example, we had this projection from A2 to A2, XY went to X and XY, right? And then inside the first copy of A2, I can take say the open subset GM cross GM. Okay, where none of the coordinates vanish, and inside the second copy of A2, I take the same open subset GM times GM, and then this morphism pi, when you restrict it to this open subset, it's an isomorphism, clearly. Okay, so this is an example of birational isomorphism. So there's a morphism that induces an isomorphism of dense open subsets. Okay. And yes.
For irreducible, it's any non-empty open, and for non-irreducible, it should be dense open. Yes.
Yes, but maybe it doesn't make much sense to speak of rational morphisms between reducible varieties, just because at the level of functions, you can consider the field of rational functions, and then two varieties are birationally isomorphic if they share the same field of rational functions, right? But if they are not irreducible, then there is no such thing as field of rational functions because there are zero divisors, and so you cannot take the field of fractions. Okay, so we only consider irreducible varieties for these things. And maybe. Pardon me? Say it again.
Почему в А2 вложено же Декартово произведение, но не равно? Почему А2 не равно ЖМ, Декарт умножить на ЖМ?
Because in A2 there are points with zero coordinates. Yeah, and in GM times GM all the coordinates are non-zero.
Спасибо.
Welcome. So there is also related notion of rational morphism, and it's used in the home assignment. So let me give it here. From say X to Y, and then it's denoted by dotted line, like this, or that dashed line. Is a morphism from a dense open subset. So we have this X, inside we have U, a dense open subset, and there is a real morphism from U to Y, but then it extends as a rational morphism from X to Y. So you see that this this dotted line does not have to be defined everywhere. It is only defined on some dense open subset. Okay. For example, there is the inverse morphism to this pi inverse. Sorry. Pi inverse. So it's not really defined. Yeah. For example, you remember that the vertical line, except for the origin itself, is not in the image. Okay, so this inverse morphism is not defined on the vertical line, but on the dense open subset, say the complement to the coordinate cross, it is well defined, and it's enough to have a rational morphism. Okay, and our pi is a birational isomorphism, so it has a rational inverse, pi inverse. Okay, so what I say is that any proper variety is birationally isomorphic to projective variety, but even better than this. I mean, there is an actual morphism. So we started from Y, and then we had this X, but it extends to an actual morphism from X to Y. So even better. Maybe let's go to the next page. Sorry. So there is a morphism f from x to y that induces an isomorphism of dense open subsets. Okay, so I mean, this is not a dotted rational morphism, but actual regular morphism. But it is an isomorphism when restricted to open subsets. Okay, so this is the content of Chow lemma, and let's prove it. So once again, any proper variety is somehow dominated, birationally dominated by a morphism from projective variety. In this sense, proper varieties are almost projective. Okay, so even before we prove this, we prove some closely related statement, but even better, even stronger statement. So let's only assume that y is irreducible and separable. So if you remember from the last time, separable means that the diagonal is closed in the square of y. Okay, and then there is a projective and irreducible variety x, and a closed subvariety z in their product.
А какое сейчас утверждение мы доказываем?
So we're proving this Chow lemma now, right? I hope you still remember it. That any proper variety is dominated by a projective variety. Okay, but birationally dominated by projective variety. This is the Chow lemma. But first we will prove some auxiliary claim. Okay, this auxiliary claim is as follows. So in the product with a projective variety, there is a closed subvariety z, such that the projection to y from z to y is birational isomorphism, and the projection to x is an actual isomorphism from Z to an open subset. Okay, so first of all, this claim immediately implies the Chow lemma. So if this is true, we believe this, then Chow lemma follows, namely, when y is proper, then the projection to y of z has the closed image, right? By the definition of being proper. On the other hand, it is birational to y, so it contains some open subset, so it must just coincide with y. Right? No, I'm sorry. Projection to x, sorry. Since y is proper, the projection to x must coincide with x. I'm sorry. Right? I mean, the other is also true, but we rather need this. And now we set f is just the inverse of the composition of projection to y with the inverse of projection to x. Okay, and this is from x to y. This is what we want. Okay, it is a nice number. Say it again.
And you make an auxiliary claim only for y separable. Is it a part of lemma that y?
There is some noise, and I cannot hear you really, Anton.
Y is separable. Do we know this from lemma statement?
That's assumed, yes. We assume that y is separable.
In lemma, okay.
Yeah, in the definition of being proper, separable is assumed. Yeah. So that's a very good point. Yeah. Maybe I should say it from the very beginning. Yeah. So where was this main theorem? Even before, yeah. Yeah, arbitrary here in the very beginning. But somehow, if it's already projective, then it's automatically separable. So where should I add it? Let me see. The image of any closed subvariety is also closed. That's true. And maybe I should add it somewhere here. And
so I just forgot
that also closed, and x is separable.
X is always separable, hence projective. Yes. So
I mean, the variety x is called proper if it is first separable, and second, it enjoys this property. Okay, but any closed subvariety of product projects to y with a closed image. Okay.
То есть в определении x не обязательно проективно?
Yeah. The general notion of a proper variety, then it's separable and has a property that projection of x times y to y is always closed. Okay, for any y. Okay.
Excuse me. And
yes.
as a question, why we can't just take this composition without y is proper? Like it's just composition of two birational things projection to X and to Y.
Yeah, but
Inverse.
we need F to be an actual morphism, a regular morphism. It is an isomorphism between some open subsets, but it is really well defined everywhere. That's what we need.
Okay.
So, but we use here that projection to X was an isomorphism, right? So we can invert it. You see here it's projection to X inverted. So I used that projection to X was an isomorphism, so I could invert. Okay. Okay. So now let's prove this statement. Okay. And so again, I take an open cover.
Excuse me.
Yes.
If we prove this statement, won't it be? Won't there be a corollary that any separable is isomorphic to a projective variety?
No, because I used that Y is proper here. You see, in the end.
You used this to construct the real isomorphism.
Yes. Yes, and what's your question? Just maybe repeat your question once again. I cannot hear you anymore.
I'm sorry. I guess I have a problem with micro. But if we use a property, we use the property to construct the real morphism from X to Y, but without it, we just have a morphism.
Any variety at all with a projective variety. Yeah, that's what you say. That's absolutely true. Yes, that's absolutely true. But somehow it's not very useful to derive some useful applications. We need an actual morphism. That is a birational isomorphism. Otherwise, that does not really work. Okay, so we take an open cover, open affine cover, like this, and then yi lies in some affine space, whatever, and sub I, and it lies in the projective space P and I. Yeah, I just add some boundary at infinity, and I can take the closure of my subvariety inside this ambient projective space. So take y bar I inside P and I, the projective closure. Okay. And now take the open subset V, that is the intersection of all those, Y1 and so on, P. It's open and dense in Y, since Y was assumed to be irreducible. And then this open subset is embedded just into its pth power as a diagonal into V into the power P. And this is embedded into Y1 times so on times YP. And this is in turn embedded into the projective closure. So Y1 bar times so on times YP bar. And here, this is closed embedding. This is open embedding. And this is again open. Okay. So hence, this open subset V is open in its closure. Well, let me say. V bar inside y1 bar times so on yp bar.
Почему там вот такие вложения, такие свойства вложения, что первое замкнуто, второе открыто?
Well, the diagonal embedding is closed just by the separable property. And what else? The embedding of open V inside any Y is open. Yeah, so the product of open embeddings is also open. And then again, the product of Y's is embedded into their closures as an open subvariety. So everything is clear, I hope. And we put we set X, the desired project variety is just V bar. Okay, so it's projected. And now, unfortunately, I must turn the page. And Z, this sort of graph subvariety, is the closure in the product X times Y of the graph of the embedding, the open embedding of V into Y. Okay. So then, just by definition, projection onto Y from Z is birational. Since if you're restricted to V, then there's just identity on V. Okay, and it remains to check that the projection to X from Z to X is an isomorphism from Z to some open subset U in X. Okay, so we have to specify this open subset, define this open subset, and so we define an open subset Zi. By definition, this is Z intersected with the product X times Yi. Okay, so we had this open cover, Y equals Y1 union so on union YP. Okay, and this is one of the open subsets in this cover. Now we wanna show that this Zi is the graph of a morphism from some UI in X, and then we will be done. So we need to show that Zi is the graph of some morphism psi I for psi I from UI into Yi for an open subset UI in X. and you see the whole Z is the union of ZI's, and then we'll set U by definition is the union of those UI's inside X, and there we are. Hence, Z will be the graph of certain psi from U to well, to Y, right? So we only have to define locally those UIs, and finally UI is by definition the intersection X with the product Y1 bar and so on, and then YI minus 1 bar, and then here you don't take closure, and then again YI plus 1 bar times so on times YP. Okay, so at the ith place you don't take closure. That's it, and the morphism psi I is just so taking the ith coordinate, so to say. Okay, and now the last thing to check is that if we have a collection of points Y1 and so on, YP and Y in ZI, then the ith coordinate YI is necessarily equal to Y, okay, to this extra coordinate in Y. So in other words, this means that ZI lies in the subset YI equals Y inside the product UI times YI. Okay, and this is clear. Because we have an inclusion in the embedding, open embedding YI into its closure, and if we take its graph, gamma, or maybe gamma I, and then it is closed. In YI times YI bar, and is the closure of diagonal. In YI times YI inside here. Okay, there we are. Nice. So this is the proof of Chow lemma, and now let's go back to this example of pi from A2 to A2, where xy went to x, y, and this morphism is the so-called affine blow up. There's a part of a real blow up, some open part of the blow up of the affine plane at the origin. So it's called blow up 0 of A2, and it projects onto A2, and it is a very important example of proper morphism. Very important. Okay, in fact, it exists in any arbitrary dimension. So let me define it in this generality. A n, and in fact, it lies in the product a n times projectivization Pn minus 1, and there is a projection onto a n from here. And it restricts to the blow-up morphism pi. So what is it? Well, from the point of view of projective n-1 space, it is just some vector bundle or even line bundle. So this 0 an is the total space of the line bundle O of -1 over P n-1. Let me say what I mean by this. So maybe more generally, a vector bundle V over some base x is an algebraic variety. P, projecting onto x, such that locally x has some open cover, maybe a fine open cover, and not necessarily, where the preimage of any open set is just the direct product xi times the vector space whatever al, and then we have to somehow glue over intersections. Maybe it will remind you of the notion of a sheaf we had at the very first class. So we have the preimage of xi, and it contains, so it is isomorphic to xi times al, and it contains preimage of xi intersected xj, which is contained in turn in preimage of xj, that is isomorphic to xj times al. Okay, and this guy is also isomorphic to x. Oh, unfortunately, I must move to the next page. So sorry about this. So the preimage of xi intersect xj is isomorphic to xi intersect xj times al, but in two ways.
L разве не равно единице?
In this particular example, it will be equal to 1, yes. But for the same price, I can give a general definition. Okay. So how ith way and j way, and the ratio of these two ways is an automorphism of xi just xj times al. So now finally the key point is that this automorphism is required to be linear in all the fibers. Okay, so you see, all the algebraic varieties are glued from open pieces. There's nothing specific about this, but the vector bundles are glued also from preimages of open pieces of the base, but its gluing is linear in the fibers. Okay, I mean, any fiber is just a vector space, k to the power l, and it's a linear operator in each fiber. Okay, and if L, the rank, is equal to 1, then V is called a line bundle. And the basic example is the base projective space, our X, and V. Well, maybe say let me say the fiber of V over a point in projective space is the corresponding line in AN, right? You remember that projective space consists of lines. Yeah, any point of projective space is a line in the ambient affine space passing through the origin. So I take this very line. Okay, so in this sense, this V is embedded into projective space n-1 times the ambient. Okay, so any point V here goes to the corresponding line, the point here, and this vector lies in the corresponding line in the affine space. Okay, fine. So V is closed in this product and given by the incidence equations. namely that we have a line P and the vector V, and the equation is that the vector lies in this line. Okay, and in coordinates you can write it down, and you will have this a fine blow-up equation, something like this. Okay, so now we have a projection from this V to the projective space, but on the other hand, we have the projection to the affine space. And I claim that this projection to the affine space is a birational isomorphism. So all the fibers of projection to projected space are just affine lines, and it's by no means a birational isomorphism. But the projection to the affine space is a birational isomorphism. Indeed, away from the origin, if you take a non-zero vector, then it uniquely defines the line just passing through this vector and the origin. Okay, so this is a birational isomorphism. And more precisely, this projection to AN is an isomorphism over the complement to the origin. Okay, and the fiber over the origin is the whole of project space Pn minus 1. Just because any line passes through the origin by definition. The whole Pn minus 1 is comprised of such line. Okay, so there we are. It's a very important example of projective and hence proper morphism. It will be used again over and over again. I think I have to stop because the time is over now. But let me just say one last word. The next time we'll start studying sheaves, because we already used the sheaves from the very beginning, yeah, because our regular functions are sections of the sheaf of regular functions by the very definition. But you see, for example, we'll need to use the sheaf of sections of this vector bundle. And you can say that functions are sections of the trivial line bundle, but this line bundle is very non-trivial, and its local sections form a sheaf. And there are many useful sheaves like this, like sheaf of differential forms, and maybe also tangent sheaf, and many things. The next home assignment I will send you tomorrow morning. So it's due in 2 weeks, certainly, and it will be about sheaves. And in 1 week, I will give some basic definitions about sheaves, but it's impossible somehow to convey the basics of sheaf theory in a lecture. So I will formally give all the definitions, but I'm sure if you don't try to think it over by yourself, it will be absolutely useless. So I urge you to try to solve these exercises before the next time, so 1 week in advance, so that you somehow get used to the sheaves. Otherwise, the next time you will be lost. Okay, so if you don't have any experience with sheaves, please just read the next chapter of Kempf book by yourself and solve all the exercises I'll send tomorrow morning. Okay, otherwise it will be a catastrophe. Okay.
Формально дедлайн остается через
Yeah,
2
the
недели.
formal deadline is in 2 weeks. Nothing. And if you know sheaves, then there is no urgency in it. But if you don't know sheaves, then please do it yourself in
So
a week. Not in 2
we
weeks.
should take exercises not from Kempf book, but from your exercises and read. Kempf
Yeah, I
book.
will send
Yeah.
some exercises from myself, but certainly it's very useful to solve Kempf's exercises, all the Kempf's exercises. But please go over the next chapter by yourself. Okay, next week I'll repeat it. But if you didn't have an experience with sheaves, you must try it before. Otherwise, you will not be able to follow next time. It'll be some formal, formal nonsense, abstract nonsense. Okay. So thank you for today. I am saving this. I am stopping the recording.
Миш, прости, пожалуйста, вот у меня такой
Yeah.
вопрос. То есть если человек прочитал главу Харсхойна по пучкам, то этого достаточно, да?
Yeah, that's more than enough. But still, just to be on the safe side, solve all the exercises I'll send tomorrow morning.
Хорошо. А еще такой вопрос. А можно присылать задачи, которые были, например, вот на сегодня, можно их прислать, например, там завтра или послезавтра?
Well, you're missing deadline, and it's not advised.
Ну хотя бы можно просто прислать и не проверять.
Well, certainly, yes, it's okay. And as a single exception, you can do this, but not as a general rule.
Okay.
Okay.
Thank you.
Welcome. So then.
Можно спросить по лекции?
Yes.
Вот в самом начале был пример отображения А2 в А2. Почему мы говорили, что плоскость без оси Y не замкнута и не открыта?
Because it's not just without vertical axis, but it's without vertical axis, but with the origin. So you remove the vertical axis, but then add the origin. And this thing is neither closed nor open, it's just constructible. Yeah.
Вот еще вопрос. В домашней работе там задача про то, что образ не содержится в линейном подпространстве. Это, то есть нельзя образ представить как какой-то, что образ не лежит в гиперплоскости.
Right, absolutely, yes. There is no projective hyperplane containing the whole image of Veronese or Segre embedding. Yes. Yes.
Спасибо.
Welcome. So if there are no more questions, then let me stop the meeting.
Goodbye.
Bye-bye.
Thank you.